Hey everybody, hope you can hear me all right. Thanks for tuning in. We're down in my basement here in St. Paul, Minnesota. Hopefully it's not too creepy. Got a little backdrop here to try to keep things coordinated. It's raining outside and the Wi-Fi is no good out there, so we're down in the basement where I had a decent anchor to do some of this stuff. So thanks for tuning in again. My name, if you don't know me, my name is Taylor Hamel. I am an arborist. I've been involved in the tree care industry for almost 20 years now. Started in 2001. Since 2016, I've been the North American technical rep for DMM International. And so I spend most of my time now on a computer or at conventions and doing things like this. So I'm super excited to be here again. I've done a couple webinars with TreeStuff before. I appreciate Nick and Kale and Carson, all the work that they put into this. So thanks, guys. And we're gonna get a kind of a slow start here, just let some people catch up and tune in. I think we've got quite a bit online already, but just a little bit more about myself quickly. Yeah, arborist and contract climber for almost 16 years or so before I transitioned into my position at DMM. I've climbed and worked in many different countries, I think 12 different countries around the world: Australia, Western Europe, UK, Canada, and of course the United States. And in my spare time, I like to play drums. Got a dissonant death metal band called Sunless. Shameless plug there. Check us out if you want to. Little bit about DMM. DMM is a company. We specialize in hardware, aluminum, steel. We do. We're very good at hot forging. We have. I guess you could say that's sort of our claim to fame is hot forging, which is forging under intense heat and pressure, and that's how we get lots of interesting shapes. And in some of our products, like the Hitch Climber Eccentric here behind me. Anyway, DMM was started as a company in 1981, and they're located in North Wales, in a little village. I'm going to slaughter the name. A little village called Llanberis. You'll have to look it up on the website. That might be on the test later. And if you ever have a chance, once this whole COVID-19 thing calms down, if you ever have a chance to be in Wales, I encourage you to visit and try to set up a factory tour if possible. It's fantastic. You can get a hold of me. I can try to set that up for you if you're ever in the neighborhood. I myself, I live in St. Paul, Minnesota. We're here in the bottom of my house. And it's pretty decent weather outside. It's raining right now, but otherwise okay. The temperature's good. So we're enjoying life outside when we can get out there. Well, let's get started. I can't remember exactly what the official title of this is, but we're going to talk about, so it's rigging. I'm going to go through some basics of mechanical advantage, how to calculate simple mechanical advantage. I won't get into the complex stuff. I might make a couple notes there. So we're going to talk about calculating simple mechanical advantage. We're going to talk about the effects of friction on mechanical advantage, because as the rope runs over a surface, it creates friction. So we need to talk about that and how that affects the output of the mechanical advantage, or the overall efficiency, if you will. Then we'll talk about forces in rope and pulley systems. So the systems that we use as tree workers, mainly for rigging, but this will also apply to some climbing techniques as well. We'll talk about forces in those systems, how to calculate those forces. Now, I'm not a mathematician. I'm a tree climber at heart, so I'm not the brightest bulb here. So I'll have some other links for you to delve into that further. I'll give you an overview to the best of my ability, but do some research yourself. That's how I learn the best anyway, is taking information from one source and then going and doing a little deeper dive on my own. So encourage you to do that. I might make some mistakes. Nobody's perfect. That's just how it goes. I've definitely made mistakes in the past. So then we'll talk about how friction affects rope and pulley systems as well, not just mechanical advantage, but say dismantling a tree, you know, a log or a branch on the end of a rope, and the different anchor points or pulley blocks or pulleys that we use for that. We'll talk about how friction affects that. And then we'll talk about some highline rigging or multiple anchor point rigging, hanging a load in between two anchor points, or, you know, speed line kind of thing. We'll dig into that a little bit. Once again, I'm not a super mathematician, so some of the physics is beyond me. I can point you in the right direction. You can go from there. So there you go. Let's start out with mechanical advantage. Okay. Actually, stop right there. We're gonna dive into some nomenclature first. All right. Hold off on the mechanical advantage. I want to talk about some of the markings that are on some of our equipment. I don't have an impact block with me, but I do have a pinto pulley here, and I'm going to turn the camera on pinto pulley. You'll notice it's got two acronyms listed here: MBS. I don't know if you can even see that. MBS, WLL. Those are some things that we want to talk about. So MBS. What MBS stands for, that acronym, is minimum breaking strength. All right. And the definition of MBS would be the load above which an item of equipment might fail when it's new, as determined by the manufacturer. Okay, that's a bit of a mouthful. MBS, minimum breaking strength, the load above which an item of equipment, when new, might fail, as determined by the manufacturer. All right, that's minimum breaking strength. Next, we have WLL, which stands for working load limit. Now, the working load limit is the load that an item of equipment, when new, can safely lift, lower, or suspend, as determined by the manufacturer. All right, one more time. WLL, working load limit. The load that an item of equipment, when new, we can only guarantee what it'll do when it's new from the factory, right? Load that an item of equipment, when new, can safely lift, lower, or suspend, as determined by the manufacturer. So in this case, pinto pulley, for example, MBS, minimum breaking strength, 50 kilonewton. WLL, working load limit, 10 kilonewton. All right, that's a safety factor of 5. That's pretty standard in hardware. And you'll notice, I don't know if you can see it on the camera, but if you do have a pinto pulley in front of you, you can check it out. Working load limit is 10, but you'll notice some arrows, and on either side of the sheave here, it says 5 kilonewton working load limit. That's because as we put 2 parts of rope in there, and we have 5 kilonewtons on either side, that'll equal our working load. Well, that's a pretty rough way of saying it, but when we'll get into that later. But overall working load of this piece of equipment, 10. And if you have 2 parts of rope, that would be a maximum 5 on either side, with some caveat in there, and we'll get into that later. Another acronym that we should be familiar with is SWL, safe working load. Okay, and the safe working load is determined by me, for example, as a competent person. I'll use that word lightly, or yourself, if you deem yourself a competent person, maybe your job site supervisor, whatever. And safe working load, SWL, is the load that an item of equipment can safely lift, lower, or suspend based on particular working conditions, all right, as specified by a competent person. So the manufacturer is not involved in this anymore. So I can take that pinto pulley and say, well, this is working load limit is 10, but you know what, this pulley is a bit used, and maybe whatever else. Maybe I've got a new person on the rope, and I want to stipulate that the safe working load for this is 5 kilonewton, 6 kilonewton, something like that. We can rate that down. We can't push it above working load limit, but we can pull it down a little bit. So pulley's been used for a few years. I would feel better if I reduced that, safe working load limit. Okay, so think about those. Those are going to be on the test. Check my notes here. All right, so let's get into mechanical advantage. Now, mechanical advantage, for it, I suppose a rough definition would be the ratio, right? The ratio when we look at, I don't have my whiteboard here. When we describe mechanical advantage, we have a number, a colon, and then a number after that colon. So it's a ratio, right? And it's a ratio of the force produced by a machine to the force applied to the machine. All right. So if I, for example, had a load here, I've got a rope and pulley system. We could call this a machine. All right. I'm gonna lift a load, and that is the output, and this is the force applied. So this is the force produced and the force applied. That would be a very simple scenario. We'll get more into that later. So it's a ratio between force produced and force applied into the system or the machine. Write that down. Might be on the test. All right. And we'll get into a little bit later how to calculate those forces and that. So I don't want to talk too fast. I got another hour and 40 minutes to go here. I'm going to take a quick sip of water. Bear with me. Okay, Kale, could you bring up my screen for me? I think I can ask you to do that. All right, wonderful. I'm going to duck out of the picture here maybe for just a minute, but if you should be able to still hear me with my microphone if my beard isn't getting in the way of it. Can you see my cursor on the screen? Yep, okay, awesome. So what we have here, this is a, excuse me. We're all good. Just turned up my brightness, accidentally hit the volume. All right, what we have here is a suspended load that weighs 100 units, depending on what part of the world you're watching from. That could be pounds or kilos or chickens or whatever you want, but 100 unit load. All right, and that's up and over an anchor point. And we're gonna call this anchor point just a natural fork, right? A natural fork in a tree, just a limb. And we've got a ground worker or whoever holding on to the other side of that rope to keep that load suspended. All right, 100-pound load or 100-unit load needs 100 units of tension on the other leg of rope. So there's 100 units of tension in this leg and 100 units of tension in this leg. That equals 200 units of tension, or 200 pounds or kilos or what have you at the top of that system. So it'd be the same thing here. I have a bag here I can lift up. Okay, that's in frame. We're going to say this bag weighs 100. I'm using 100 units of tension in this leg of line to keep this aloft. So 100 plus 100 equals 200 up at the anchor point. All right. Now, that is the ideal scenario, assuming that there's no friction. All right. But we live on planet Earth and there's gravity and there's friction. So this rope running over that anchor point, there's surface friction up there. So that's going to affect the load on the anchor and also how much tension I'm going to need to put in to this leg of rope in order to manipulate this load. So everything just sitting here with no friction, 100 tension in this leg, 100 tension in this leg, 200 at the top. Now let's change that up a bit on the computer program here. All right. Now, you can see there's some changes. I hope that comes up on your screen. Kale, are you able to see all those numbers? Okay, cool. So we still have a 100 unit load, and there's still 100 units of tension in this leg of rope between the load and the pulley here. But instead of running through a natural fork now, what I've done is I've put in a high efficiency pulley. So something like a one of our Pinto rig pulleys, or a gyro pulley, something like that, high efficiency, maybe an impact block. And I just dialed up the friction to 13%. So there's, okay, hang on, sorry there, I'm jumping ahead. I want to do this other one first. There we go. Okay, my bad, I jumped ahead. Now, back up. Reset your brains like I had to reset mine. We're back to a natural crotch here. We've got 100 kilo or 100 load, 100 tension in this leg of line, and we go up and over a natural fork. Now, a natural fork, depending on the size, will generally have about 50% friction there. All right, meaning that the rope, as it runs over that surface, has to deal with that surface friction. And if I am lowering this load now, what's happening is that friction up top is doing some of that work for me, and thus I need less tension in this leg of rope. So whereas previously it took 100 pounds of tension to hold 100 pounds in the air or manipulate 100 pounds, now with that friction, it's only taking me 50 pounds to manipulate this load. But there's a stipulation there, okay? I'll keep that up on screen, and then I will explain this. Or maybe it can't be. We can't have two screens up at once, can we? Oh, maybe we can. Kale's really good at that. I'm terrible with technology. Now, we're going to take that same load, okay, 100 kilo load here. I'm just going to use kilo, pounds, whatever, interchangeably. I can't keep it straight. 100 load, 100 tension. There's always 100 tension from the anchor point to the load on this leg of line. Now, with friction there now, as I go to lower this load, right, that friction over the top of the anchor is doing some of the work for me. So I only need to hold on here now with 50 pounds of tension to lower 100, okay, because that friction is doing that work for me. I'll get my scale up here, and we'll see if I can zoom in on it in a minute. I've got some heavier weights that we'll put on there. So just bear with me. You'll get a live demonstration there in a minute. So lowering this with friction at the anchor point reduces the amount of tension I put in. 100 pounds tension here, 50 pounds tension here. That's only 150 on the anchor point, whereas before with no friction, it was 200. So right here, adding friction to that anchor point in a lowering situation, we're reducing force on that anchor. But it changes when we go to raise it. Let's see if I can find, there we go. As it pops up here, now, same load, only 100 units. Still 100 tension in that leg of rope. We go up over that natural crotch, and now we're trying to raise that load. And you'll notice I need to use 200 pounds of tension now in order to raise that load. And that's because I am working against the friction that's at that fork. And you'll notice anchor point load now is 3. All right, that's significant. We went from lowering 150 on the anchor point, now raising. Not only is it nearly impossible for me to do it, 100 pounds tension, this never changes, but the tension here changes between lowering 50 pounds and raising. Now 200 pounds of tension in this leg of line to raise that 100 load. And then again, 100 plus 200, we've got 300 at the anchor point. Significant change. Very, very dramatic. So let's do that in real time here. I'll see if I can zoom in to the, so you don't just take the computer's word for it. I'm going to lift up 70 pounds here. It's all I think my ceiling will handle. But it's all just numbers and the math works out. And really 70 is about all I can lift. So here we go. Now, Kale, you're going to have to help me out here and tell me when you can see the numbers. When you can see the numbers on this load cell. And maybe you won't be able to see them at all, which is unfortunate. I just don't have another way to do this. Okay, you can see those numbers there? All right. I might have to get creative here with a stand. Let me try to get as close as possible here.
Just don't break my camera.
I won't break your camera. Can you see those numbers, Kale? Okay. Okay. Cool. So I'm just going to get this up in the air slightly just to show you what it weighs. So you know I'm not fibbing about it. Should be about 70 pounds with a little bit of gear, so it might be like 73 pounds. Yeah. Can you see that? 73 pounds. Okay, everyone can see that? And that is simply just, I've got two dumbbells suspended here. All right. How to read numbers with Taylor. All right. So what I'm going to do, pull this up in the air. And now, if there were no friction here, so I've just got a carabiner. If there were no friction here, 73 pounds should take me 73 pounds for a total of 146 pounds at this anchor. All right, let's just see what it comes out to. Okay, I've got that suspended, and I'm just holding on as lightly as possible. And what are we showing there? 109. Can you see those numbers? Okay, sweet. 109. So I'm just going to lower this in a nice controlled manner, slowly. And what do we end up with? 108, 107. Okay. So 73, so 108 minus 73, that ends up being about 35 pounds ish. Is my math on the fly working? Yeah, so so I had 73 pounds, and if we add those together, right, 73 pounds plus what I was holding on to, in this leg of rope was about 35, which gave us 108. Yeah, does that jive with everybody? Okay. 73 pounds tension here, 35 pounds tension here, roughly 50%, which is interesting to know that if you run a rope 180 degrees over an aluminum carabiner, you get about 50% friction. Interesting, isn't it? All right. Now, what can you guess the load will be when I try to raise it? Okay, just keep in mind what we saw before on the computer screen there. All right, here we go. I'm going to just try to do this in a controlled manner, and hopefully the anchor doesn't come down on my head. I should probably have a helmet on. All right, here we go. Raising 73 pounds. Okay, 205. Oofta. All right. 73 or 205 minus 73, that gives 100, roughly 140. A little bit less, 135 pounds, right? So double that. Hope that's coming through and making sense. Huge swing in anchor point forces there and in the amount of tension that I had to put in. So once more, slowly lowering 73 pounds. Takes me about 35-ish pounds to control that. Okay, and now we're going to change and we're going to raise it. Right, 200 some-ish pounds. Okay, right there, right before your eyes, notice it change. Now I'm lowering it. Okay, now I'm raising it. So there is friction for you. And friction's not necessarily good or bad, it just is there. And so it can work to your advantage or your disadvantage. It's a disadvantage for me to try to lift this with a lot of friction, but it's actually quite helpful for me when I lower it with friction, because that friction is doing some of that work for me. It's easier on my body, less force on the anchor points. And if we get this up here a little bit, I'm going to show you that surface friction working by the rope isn't going to move at all, but I'm going to change that load. So right now I'm just working with that friction, increasing. The rope is barely starting to move, right? But the load hasn't moved at all. And now I'm releasing. You can see those numbers changing right in front of your eyes, right? Without the rope moving at all. So that's friction. That's friction manifest right there in front of us. Okay. And I just got a alert that my battery is running low on my computer. So I'm unfortunately going to need to run away for 30 seconds. I'll be right back and grab this charger so we don't die. Okay, there we are. Sorry for the interruption. We're good to go. Let's go back to the screen now, and we're going to drop in. Where are we? There we go. We're going to put a high efficiency pulley in place. So you can see on the screen, same scenario. instead of the natural union, we've got a high efficiency pulley in place. And I just randomly, not randomly, I arbitrarily typed in that it has 13% friction, which is about what one of our gyro pulleys has. So let's assume this is a DMM gyro. We've got 100 load, still 100 tension between the anchor point and the load. That'll always be the same. We've got less friction over top. And in this case, we are lowering. So some of that friction is doing the work for us. We've got 87 pounds to lower 100. Whereas with 50% friction at the top, we only needed 50 pounds. All right, that's a lowering situation. Now let's keep the same pulley in and raise it. There we go. 100-pound tension, always the same in this leg of rope between the load and the anchor point, or the pulley in this case. Little bit of friction overcomes, so we need slightly more than 100 pounds to lift it. We got about 115. Okay, so what we've got there is an easier time raising and a little bit of a harder time lowering than versus high friction. So back up to the load cell here. What I'm going to do, if we can recall our numbers from the first lift with just the carabiner, 73 pounds. When I lowered it, we had about 105, and when I raised it, we had about 205-ish. All right, let's see what happens now when I put in a high efficiency pulley like this gyro. It's got ball bearings in it, got a slightly bigger sheave. All right, so we'll lower first, and already I can tell I have to hold on with a lot more tension. So I'm going to just lower it ever so gently. What numbers are we looking at there, Kale? Can you see? Okay, 130. So there's slightly more force on that anchor point, slightly more tension that I have to put in this leg of line, because when in that lowering situation, because the pulley's not doing as much work for me in terms of friction, right? There's less friction there. So I have to generate the friction or the tension in my hands and in my leg of the rope. All right, now let's look on the way up. Now this already feels easier. Just going to go gently, nice and slow and controlled. Okay, 157, 158. All right, quite a bit of difference between when we had a lot of friction in the carabiner. Almost a 50-pound difference just with a 73-pound load. So I hope that's clicking, that friction, it's not good or bad, it just is what it is. It either works with us or against us, depending on the situation. But it also very much depends on whether you're raising something or lowering something in this scenario. All right. So it's not always good, not always bad. Just think about it that way. I hope that came through in those live examples and on the computer screen. Cool. Yeah. Okay. Sure. That good one, Kale. Did that come in from online, or did you just think of that?
We have Ryan De Silva asking if you have a bigger bend radius at the friction point, does that mean that you could potentially exceed 50% on that efficiency number?
Okay, got ya. So in just my experiments that I've done with a load cell and some natural forks, some natural crotches, branches, whatever, I found that within a certain diameter range, and really regardless of the bark, it might be a really thick barked, cottonwood or versus very smooth barked plane tree or something, platanus. Even, bark will have a little bit to do with it, but yeah, in general, over a very wide range. And I don't have a scientific study, but just what I've done at the places I've been, quite a wide range of branch diameters have about a 50%. Have about 50% surface friction. The same thing with a ring and ring friction saver, an aluminum ring and ring friction saver really has about 50% friction. And as we could see in the example here, just an aluminum carabiner has about 50% friction. So if I added 2 or 3 carabiners together here, I would imagine it would be about the same 50% friction. I don't know where that threshold is, where it starts to create more or less. In some cases, over a very, very tight bend radius, you're creating more friction. Just because the rope, you're pinching, you're bending the rope so much. It also depends on the diameter of the rope. If I had a 1-inch bull rope in here, or a 24 millimeter bull rope in here, it would generate much more friction than, say, a 2 millimeter Dyneema throw line, right? There'd be much less friction there. So it really varies a lot. And I guess what I'm trying to do in the live examples here are just, work with material that we normally work with as arborists. So, just a whatever 11 mil climbing line, 1/2-inch rigging rope, whatever. So yeah, that's that. I hope that answered that question for you. Oh, I just ducked down for a minute here. So let's keep moving on. We got time flies when you're having fun. Let's talk about. Oh yeah, we're gonna keep it live here, and I'm gonna back this up a little bit again. So you can all look at my wiring work. I didn't do it. Okay, we're gonna go back to the climbing system. Now, speaking of mechanical advantage, that was a demonstration of friction, the effects of friction in rope systems. So let's back up just a tad and talk about mechanical advantage. So here I have a whatever, your standard moving rope climbing system. So we've got 2 legs of rope, we've got a terminated end, we've got an anchor point, whatever it happens to be, and a pulley to use as a fair lead. Okay, so right now, sure, we all know how that works. You shorten it and lengthen it, you climb around on it. But did you know that you have a built-in mechanical advantage system here? Okay, and this is something that I've said in the past that I was wrong about. I need to come clean, tell everybody that I learned a lot over the years, and when you as a climber are tied into this system, yeah. Ooh, there goes the yeah. Let's look at it this way. If I disconnected and attached this to myself, and I had a friend lifting me up, right? A friend pulling me up into the air, right? That would be a 1-to-1. Assuming no friction, that's a 1-to-1. I've got my body weight here, and they have to pull with that same amount to raise me up into the air. Okay, 1-to-1. When I am connected into the system, and I am the load, and I am also the input force, the one making the input force, that changes things. Now, when I am connected to this and I'm pulling myself up in the air, that is a 2-to-1. Okay, and I argued against that for a long time until I finally pulled my head out and stopped arguing it. Okay, call me a conspiracy theorist, but I'm coming clean now, everybody. I was wrong. So now, if I am a climber in a tree and I'm injured and I can't move anywhere, I'm stuck, a rescuer can come over here and simply pull that tail up through that pulley, right? And now we've got a rescuer, not myself at this point, but a rescuer could haul up on this line, and this is a 3-to-1 mechanical advantage, just like that. And how we calculate that mechanical advantage, this is a simple mechanical advantage system, right? This is you could call this a block and tackle, okay? A block and tackle is a system of pulleys with rope or cable reeved in between them, used for raising loads or pulling things, right? A block and tackle is a system of pulleys with rope in between them used to move things around. That might be on the test. All right, so we've got a 3-to-1. And how do we quickly determine 3-to-1? All right, we count. Let me define a simple mechanical advantage. We have an anchor point that is not moving, and we have a moving block, which is generally where the load is attached. So I want to lift this load, which will be this bag here. If you can see the bag in the screen, kind of. All right, we've got 2 legs of line coming down. We pull this tail up, and I'm pulling upward. We now have 1, 2, 3 legs at the moving block. 1, 2, 3. That's a 3-to-1 ideal mechanical advantage. All right, and an ideal mechanical advantage is assuming no friction. All right, but as we saw earlier, friction plays a big role in the output of a mechanical advantage system. 1, 2, 3 legs at the moving block. All right, some further definitions of mechanical advantage. We have an input force, right? I am inputting force into this system. That's my input force. We have a reaction force. That is, in a simple system, that is the force at the anchor point, right? Input, reaction force, and output force. The output force is at the load. Okay, we'll get a little further into that in a minute. So, what are some ways that I can make this system more efficient? All right, I want to reduce friction. I've got a nice pulley here, the hitch climber eccentric with a ball bearing in it. That's very efficient. But right now I'm just through over a natural fork. So what can I do to make that system more efficient? I could put a pulley up there. For example, I don't know, a pulley saver, or in this case, I've got a, you probably can't see it's out of frame now, but there we go. High efficiency pulley. I've got greater efficiency there. Okay, reducing friction in a system like this, just like when I was raising and lowering those loads, it directly affected how much tension I had to put in my hands. And in this case here, with rigging, or in a climbing system, for example, now the friction hitch is taking more friction, right? It has to deal, that friction is concentrated here now on the friction hitch because it's not concentrated at the top anymore. Back to natural crotch there. Simple mechanical advantage. Give me 1 second here. I'm going to set up a block and tackle. Slightly different block and tackle. All right. That ought to work. So here we have some gyros. I managed to forget to grab the other twin gyro, so I'm just sticking 2 of them down here on the bottom. Don't mind me. All right, this is pretty standard. Should I tip that up a little bit, Kale? There we go. We've got You call this a fiddle block, a set of 4s. And we have double sheave pulley, and we're going to raise a load here. So I've got this raised so that I've got it rigged so that I can pull downward, right, to raise this load. So I have an input force, I have a reaction force, and I have an output force. All right, now the ideal mechanical advantage here is what? Don't everybody shout at once. All right, should I take a Q&A, Kale, or just keep going? Yep. Yep, we'll get into angles. Okay. Oh, good. Hi, Courtney.
She was the first
If
one.
that's the Courtney I'm thinking of, you're not. You're here in Minnesota. So in this case here, I have this rigged. I put my input force in, and I count the legs of rope at the moving block. And right now I have 1, 2, 3, 4 legs at the moving block. So the way I have this rigged right now, this is a 4-to-1 ideal mechanical advantage. 4-to-1. Now, if I were to flip it over, bear with me. Okay, same system. Never mind this, it's a little bit ugly. I know I'm the DMM rep. I should have had a double sheave pulley. It's at my storage unit, and I forgot it was there. So here we go. Same system. Now, input force, moving block, 1, 2, 3, 4, 5 legs at the moving block. Now we have, this is rigged to a 5-to-1 ideal mechanical advantage. Input, reaction, output. So ideally, this would be input of 1 unit, reaction of 4 units, and output of 5 units. So let's just say this weighed 100 pounds, okay? Ideally, with no friction, 100 pounds, I put in 5-to-1. I would need to put in 20 pounds of tension in order to get this moving. Now, that 20 pounds now has gone into my body. That mass has transferred into my body and has reduced force on the anchor. So we've got 100 tension here, 100 load, 20, 80. And we can just count the legs of rope. 20, 40, 60, 80, 100. 20, 40, 60, 80. So that would be 5-to-1. So a fiddle block like this, depending on how you rig it, or how you rig it, you've probably heard the term rigged to disadvantage. You can call it that if you want, the other way around, but just depends on how you rig it. So 5-to-1 here, 4-to-1 the other way around. And as we're expressing mechanical advantage here as a ratio, it's always input to output. So this is 5-to-1, and the other way around is a 4-to-1 because it's based on the input versus output. Okay. Now let's take friction into consideration. It'd be great if I had this on the computer screen, but I just had to buy a new computer yesterday and dump all this into it, so I didn't get around to it. So let's just look at it. Let's look at it this way. And what I'm going to do is put this back to that 5-to-1 advantage. or yeah, 5-to-1 M8, mechanical advantage. Okay, now let's put friction into the equation. So ideal mechanical advantage is the mechanical advantage considering no friction. The actual mechanical advantage, the AMA, so there's ideal and actual. Actual is what really is happening in the world considering friction and bend radius and the type of rope and rope stretch and all of that stuff. So let's get into calculating the actual mechanical advantage at this point. My notes here. Okay, so I've got a load of, we'll just make it easy, got a load of 100. And let's, just to make the math easy, let's say that each one of these sheaves is really, really efficient and only has 10% friction. Okay, so, and this is going to be on the test, 10% friction in these sheaves. Let me turn this around again. All right, so I make my input, 100 pounds. Okay, back up 1 minute. It's easier to work backwards. Let's say I put in 100 pounds of tension. Whatever this load weighs isn't important at the moment. I'm putting in, because this is how my brain works, because I'm a simple math guy, 100 pounds of tension going into this leg. That's my input, 100. Now, as that rope goes over that sheave, there's 10% friction there. So I lose 10%, if you will. I lose 10% to friction. Okay, input 100. As soon as this rope comes out of that sheave, the tension in this rope is now 90, right? 100 minus 10%, that's 90. 90 tension here, goes over that sheave, loses 10%. 81 tension in this leg. Goes over the sheave, loses 10%. 81 minus 8.1 is 73. Am I right? Okay, 73 tension. Up and over that sheave, loses another 10%. Down here, and now we're at 66, something like that. Okay, so you can see the actual mechanical advantage, the actual output is greatly affected by that. It's not 100 tension in every leg anymore. So if we add all those up, I've got 100 input and whatever those numbers come out to be. It's not a 5-to-1 anymore. All right, and I apologize, I don't have that up on the screen. Am I making sense there, Kale? Can you track that? Yeah. Okay. Yeah. Right? So 100 tension, friction, got lost, less tension, friction, less tension, friction, less tension, less tension. It's not just 100 multiplied by 5 anymore. All right, so I'm going to quickly do a calculation here. 100 plus 90 plus 81 plus 73-ish plus 66. All right, it's actually a 4-to-1. I've got roughly 410 output with 100 input. Okay, not a 5-to-1 anymore. Still pretty darn close, but in reality, a 5-to-1 is never actually a 5-to-1 because of friction. All right. I could do that. Yes, that'd be a good idea. Thank you. Oh, okay, cool. Oh, you're going to make me work, Travis. Ugh, this is the most lifting I've done in a long time. Ugh, okay. And then the load cell. Oh my gosh, that's heavy. For an office guy, now I'm a desk jockey.
Most people are desk jockeys now.
Yeah, that's right. We all are right now, aren't we? Or we should be. Okay. All right, let's zoom in on these numbers. Slide everything forward here again. Got an okay view there, Kale? Okay. So we're back to 73 pounds. I'm going to lift and we'll take that 73 minus what's up on the screen there will be what my input force is. Okay, 54, 53, 54. Okay. 73, 54. What was that? 19 pounds? Or am I totally lost my mind? 73 minus 54, 19. So then we have 73. Okay, 73 divided by 19, and we come up with 3.84, 3.85. All right. So that, you know, you got to take this with a grain of salt, everybody. This is a very low load. Things change, but you know, if that load were higher, we would get a higher efficiency out of this system. We've just got, there's a lot of rope weight and all that stuff with such a low load. That's probably not quite accurate in terms of gauging the efficiency of these pulleys. We should probably be using like 100 kilograms or something, but it just goes to show what we would assume. Well, what is ideally, the ideal mechanical advantage is 5-to-1. The actual mechanical advantage here that we just expressed with this load was just about 4-to-1, 3.8-to-1. All right, 8.5-to-1. So significant difference, yeah. And we could do the math and figure out all the the efficiencies of those sheaves if we wanted to really dig into it. But point is, just because ideally it's a 5-to-1 does not mean it is in real life. So don't get yourself into trouble like I've done a few times. Cool. Yo, try not to drop your computer. Okay, I'm seeing little messages on the screen, which is funny. Where am I going? I'm trying to get back to normal here. Okay, how's everybody doing? Everybody hanging in there? Got about 45-ish minutes left. So there you go. Mechanical advantage. How to calculate it? Input force, reaction force, output force. Count the legs at the moving block. 1, 2, 3, 4, 5. We got a 5-to-1 here. Ideally, actual mechanical advantage, you would have to measure it like we did here. Okay, let's move on to rope systems. We'll move into vectors now. And the weights go down there. Okay, ducking out of sight here for a minute, going back to my screen. I'm probably talking very loud in the microphone and I don't need to. Let's look at a 90-degree redirect. I'm going to take a sip of water here. How long is that break? Is it imperative that we take a commercial break? Okay, Kale's talking to me about a commercial break. We'll do that in a minute. Let's look at what we have up on the screen here now. And while we do that, prepare just another quick. Okay. All right, on the screen, you can see here, we've got our load again, which is 100. We've got 100 tension in that leg of line. We're going up through an anchor point at 90 degrees. Cool thing about this program, I can show rope angles here. There we go, boom. So you can see we've got 90-degree angle there. Now, this is assuming no friction. So this is, I've got the friction turned off. And at a 90-degree redirect, I just have a hand here. This could be another anchor point. It could be terminated there, whatever, it doesn't matter. But what we're looking at is this angle, the reduction in force at the anchor point as we take that and open that angle up versus where the hand just down here, as we showed earlier. Okay, so at a 90-degree angle with no friction, we've reduced the load on the anchor to 141 pounds versus 200. All right, now that 141 pounds, that is acting in a direction, and that is a vector, right? So that big red arrow you see there, that is the direction that 141 pounds is acting in. We have a vertical load of 100 pounds. We have a horizontal load or force on that anchor point of 100, but the peak force is acting on an angle that bisects those two sections of rope. So at a 90-degree angle without friction, that peak force is happening at 45 degrees. Now that has a significant impact on how we need to think about rigging in trees. Okay, we can look at that on the screen and say 90-degree redirect reduces force on the anchor. All right, but that force is acting in a direction like we saw. So let's say I have a tree branch. I'm going to try to simulate this. Right, I have a tree branch sticking out at 45 degrees, and I'm going to put a redirect out here, or my rigging point. Okay, trying to get this on screen for you. So this, in this scenario, is a you'd call this a strong anchor point. This branch is connected back here at the tree. I've got an anchor point back here, and we've got our load. Maybe we rigged off the end of this branch and we're lowering it down. All right, this is a strong situation because that peak force is bisecting those legs of rope and compressing that stem. All right, that's a very strong anchor point in that case. What the opposite would be if my how am I going to do this? Here's my rope, my branch again, 45 degrees. I have an anchor point over on the other side out here. Now what's happening is when that load comes on, we're flexing this anchor point. Okay, they're both 90-degree redirects, but one is very strong and the other one is torquing that limb and not using that tree structure to our advantage. We always want to use that tree structure and our rope placement to our advantage. So hopefully that made sense in my weird little arm branch explanation. Now, we also need to think about how friction affects that. And I think we'll do it on the computer here first, and then I'll do it live. So we're going to turn on some friction, and we're going to pull. All right, it's barely noticeable, but you notice my little arrow moved a little bit. What we've got here, I've added friction into here, so we're going to call this a natural fork, natural crotch friction again, which has 50% friction, roughly. But now we've opened this angle up a bit. We're not bent over that at 180 degrees anymore, so we need to reduce that friction a little bit, and I've reduced it to about 25%, just as a rough estimate. I don't know if those numbers are too small, if you can see them on the screen. Kale, can you let me know? It says 167, vertical 100, horizontal. Okay. And that angle, so I've got 25% friction, and that angle you'll notice says 53.1. So what's happening here is always between the anchor point and the load, if there's nothing else in the way, that'll always be 100 tension, right? In this case, we've got a 100-pound load. Whatever your load weighs, that leg will always have that tension in it. Now, as we go over that natural fork and we're pulling, you can see the hand here is pulling, we're raising this load. We need to overcome that friction, and we're putting more tension in that leg of line, 133 pounds in this example, which then puts our peak force at 167 on the anchor point. But that peak force is happening now not at 45 degrees. We still have a 90-degree angle here, but because there is more tension now applied due to friction on this, there's more tension in this leg of rope due to the friction on the anchor point, that moves that peak force over toward the hand a bit. Okay, not significantly in this case, but if there was a lot of friction there and a heavier load, you might be moving that quite a bit. So I hope that's making sense to everybody, and we'll try to do a live demonstration of that. Now let's reverse it and lower the load. Here it comes. Boom. All right. Still 100-pound load, 100 pounds of tension. We've got some friction in the anchor point doing some work for us. So as I lower this, I only need to use 75 pounds to lower the 100. We reduce force on the anchor point even more. And that peak force, that peak vector is moving closer to the load because there's more tension here than there is here. All right. So let's look at that, try to look at that in a live example. I'll try not to kill myself here. This is actually quite difficult to do. We might not be able to, I'm afraid we might not be able to see this in the camera. But let's look at it in terms of, boy, yeah, that's going to be hard to see in the camera. But what I want to do, we probably won't be able to see the loads as I do this. I'm just not set up for it. But what I want you to look at is as I'm raising and lowering, I want you to watch this chain of hardware here. That is always going to point at the highest force, at the peak vector. Okay, so as I just lift this straight up and down. Well, I probably don't need to do it with 75 pounds, but all right, as I'm just holding this straight up and down, our vector is just straight up and down. There's nothing else going on there. As I knock my computer over, I'm going to move out of frame here. All right, as I start to, and maybe you'll be able to see the camera. It's hard, or the the load cell, but now as I move away and open up that angle, I'm reducing force, but at the same time, I'm changing the direction that peak force is occurring in. I'm changing that vector, okay? And that has an impact on, again, on tree structure. So here I'm greater than 90 degrees. Should I move the camera, Kale, or can you? Yeah, okay, hang on. Try to, ooh, multi-talented. You get a look at my plumbing. All right, we'll try that. So here I am, a little higher than 90 degrees. I'm using some boards here to help me. But as I lower this now, watch how the load cell moves closer to the load, right? And boy, this is going to be really hard for me to lift. Hang on. This is always the hard part. So as I raise, whoa, I'm picking lighter weight next time. Oh my gosh. Not a bad idea. Okay, so here, now we've got it held in place. I'm going to pull, right, and raise the load. I've got my foot against the, right, and now as I lower, look at how drastically that angle changes. Okay, now here I'm going to raise again, right? Okay, same degree. It's the rope angle isn't changing, but the vector, that peak force is occurring. That's changing drastically based on whether I'm raising or lowering, and that's friction. So here I have to overcome friction. Much more tension in the top and the horizontal leg of rope, and now there's more tension in the lower leg. Always 73 pounds in that vertical leg, but I'm just adjusting how much tension is in the leg that I'm holding on to, and that in turn is affecting the vector there. So I'm just going to do this one more time, and just before I throw a pulley in here, and just look at how much it swings. So here I'm just lowering it gently, and now it's going to swing toward me quite drastically. I don't know what that angle is. It's got to be a good 30 degrees. It's probably changing. All right, now hold your horses. I'm going to throw in high efficiency pulley, and if you could see the load cell, the numbers would be different. But now let's just look. Now this is going to be easier for me to lift, harder for me to hold on to, but the swing should be much less pronounced. So about that angle, and now about that angle. All right, much less swing in the load cell because there's less friction, so there's going to be less change in vector at that anchor point. I hope that's making sense to everybody, and that's very clear. Would you say so, Cale? Okay. Okay. So there it is, very little movement in very little change in vector. One last time. Got to put my foot up here again because this is much harder to do. Okay. There we go again. Big, big, big change in vector due to the friction. And that's enough of that. Okay. Whew, hope that made sense to everybody. Got about a half hour to go here. Do you want to take a commercial break, Cale? Yeah, let's just do that. This is a good point to do that. And maybe people can chime in with questions. Looks like we're going to a commercial break, folks. I'll see you soon.
We have a bunch of great webinars just like this one scheduled on our Facebook page, so make sure to RSVP to the Facebook event pages for updates. On April 2nd at 6 p.m. Eastern Standard Time, plant healthcare expert and arboriculture historian Joe Aiken will be giving a webinar on proper fertilizing for creating healthy foliage. There will be 2 free CEUs available for attendees of this webinar. On April 23rd at 6 p.m. Eastern Standard Time, David Anderson of Canopy Watch will be giving a great webinar on canopy exploration techniques and conducting science in the trees. David has some unique experiences in arboriculture, so this is going to be a super interesting webinar. There will be 2 free CEUs available for attendees of this webinar. On May 14th at 6 p.m. Eastern Standard Time, plant healthcare expert Trent Dix will be talking about preparing for the newest invading pest in the U.S., the spotted lanternfly. This webinar will have a lot of important information about battling the spotted lanternfly, so be sure not to miss it. There will be 2 free CEUs available for attendees of this webinar. Keep checking our Facebook events page to stay up to date with all of the great webinars that are on the horizon.
Hi, I'm Cale Royer, head party animal at TreeStuff.com. I'm here to make sure that everyone knows about our TreeStuff party program. Each month, volunteer arborists from different regions host free recreational climbing events powered by TreeStuff.com, giving local arborists a chance to meet, hang out, climb, and try out some cool new gear in the trees. Every TreeStuff party is 100% free, so there's no reason to not bring your family, friends, co-workers, and acquaintances. Check our Facebook events page to learn about upcoming TreeStuff parties, and sign up to be notified when there's a new TreeStuff party in your neck of the woods at treestuff.com/parties. It's all about seeing friends, making new friends, and having fun in the trees. I hope you can make it to a party soon.
The North Carolina TreeStuff party has been rescheduled from April until August 1st. It's hosted by Nick Johnson in Waynesville, North Carolina, and will go from 9 a.m. to 3 p.m. On May 9th, TreeStuff superfan Jason Dudek will be hosting a party in Mukwonago, Wisconsin, near Milwaukee. Jason's party will go from 10 a.m. to 4 p.m. For more information and addresses, head to our Facebook events page. You can also get more information about these and upcoming TreeStuff parties by going to treestuff.com/parties. On Tuesday, March 24th, we'll be hosting a free conference call with Nick Araya on how to bid tree jobs. There are 3 sessions available. They'll be 30 minutes long, and each has a limited number of spots. Visit our Facebook events page for more information and to get your free tickets. Trio caching is a fun TreeStuff program based around searching for hidden treasure in the trees. Volunteer arborists from around the world have set caches in their area for climbers to seek out using GPS, their wits, and their climbing skills. To start trio caching, all you have to do is go to treestuff.com/triocache and find a cache near you. We have a few new trio caches to announce. Brandon Othen of Arizona has set Trio Cache 87 near Phoenix. Sid Howells of Social Climbers in the UK has set up 2 trio caches, number 108 near Southampton and number 109 near Guildford. If you'd like to find these caches or any of the other caches around the world, you can request the coordinates at treestuff.com/triocache.
I'm Carson with TreeStuff.com, and I'd like to ask you to take a second to learn about the Fallen Families Fund. It's a charity created to provide small cash donations to families who have been affected by the death or injury of a working arborist. All of the administrative costs are covered by Cheryl Inc., so 100% of your contribution goes to help families in their time of healing and recovery. You can learn more and donate at www.fallenfamiliesfund.org.
Very first thing up top is my PPE. I keep my helmet in here, a nice clogger buff. Keep my helmet right where I need it at all times. After that, pop open my interior compartment and we'll take a look. First thing on top is my saddle. Keeping my tree motion, has my lanyard on here, bloodstopper pack kit, akimbo, and everything else that I could possibly need for a day in the trees. After that, I have my chainsaw lanyard, my Saka Neoscinder, a pulley saver for when I'm climbing double rope systems, handsaw, 1 cube, 2 throw line cubes, a zigzag with a chicane, and then my climbing line in the big bag. And inside my climbing line, I've got a Sterling SRT line with a zigzag and chicane on that as well. Notch, wedges where I'm in the tree, extra foot loops for my socket, my med kit, and because I'm allergic to bees, I carry my EpiPens. In the very front of my notch bag, I've got a collection of hardware, some thimble, Prosix, a notch throw bag, some extra cordage, and a quickie tool for when I'm using my rope runner. This is my notch bag and all the gear I keep.
I made it. Hey, we're back. Cool. We got about just under a half an hour to go. I want to comment briefly on something that I wanted to touch on before, and that is back quickly to mechanical advantage. Get my camera back here. One thing about mechanical advantage, and this is applicable in the real world. Say you're pulling a tree over, okay, and we've got this fiddle block set up to pull a tree over, and we've got it anchored to the base down here, and this portion is attached to a rope, up at the top of the stem, pulling a tree down. We've all done that, yeah, pulling a tree over. So just imagine this is anchored at the stump or whatever over here, and this is anchored to the top of our tree. So bear with me. You're going to have to imagine. Yeah, there we go. This is the base, and then we're attached up here, and we're going to pull this tree over. How do I want to set this up? That'll probably work just like that. So attached at the base, pulling this tree over. Now we have 4 pulleys here. We have 4 sheaves, but let's say we're in the field and we got to build this out of 4 separate pulleys, okay? And we have 3 kind of cruddy pulleys that have been rattling around for a long time. They're not very efficient. And we have 1 really, really good, brand new, excellent, high efficiency pulley. So we're building a block and tackle, which is a series of pulleys with rope reeved in between them, okay? In this case, we have this set up to pull at a ideal mechanical advantage of 5-to-1, because I have this anchored at the stump, and this is anchored to the top of the tree that is going to move when we pull it. All right. Stationary anchor, moving block. We can count the legs at the moving block. 1, 2, 3, 4, 5. All right. We've got an ideal 5-to-1. But so and we need 4 pulleys to put this together. We have 3 cruddy pulleys and 1 really good one. Where are we going to put the good pulley to maximize the efficiency of this system, to get the greatest output of this system? Where is that good pulley going to go? All right. Is it going to go as close as possible to the input? Is it going to go right here, right before, or right after my input? Is it going to go somewhere in the middle? Or is it going to go at the very end, closest to the load, as it were, okay? So have a think about that for a minute.
Don't need to.
And then I'm going to have to tell you the answer.
Jay Bradley already says anchor.
Okay, somebody guessed anchor. Are there any more guesses?
Ryan De Silva said close as possible to the input.
Okay, we've got one anchor, we've got one input. So let's think about it this way too. Input is, we'll call that pulley number 1. So first pulley number 1, pulley number 2, pulley number 3, pulley number 4. All right. So if I want the best possible efficiency out of that system, where should the highest efficiency pulley be? Pulley number 1, right after the input, 2, 3, or 4? Think about that for a second.
Courtney Johnson says pulley number 1.
Pulley number 1. Okay.
Andrew McCoffey says furthest from the input.
Furthest from,
Marvin
okay.
Budd says close to the load where the highest stress is.
Okay. Cool. This is great. I like this interaction. That's really nice. Well, let's go back and remember what we learned about friction in those pulley systems. So let's just pretend now, for easy numbers, each of these sheaves has 10% friction loss. Okay, they're very efficient, but there's 10% friction loss. If I input 100 tension into this leg, okay, and that efficient pulley is 10% right there. The rest, let's call them really crummy, and they only get 50% efficiency. Okay, so 100 tension, 10% loss, 90 tension. Now we lose 50%, and we're down to 45. We lose 50% again, and we're down to 22.5. We lose 50% again, and we're down to 11.25. Add all those up, and you get this number. I'm going to put in my phone. 100 plus 90 plus 45 plus 22.5 plus 11.25. You've got a 2.68 to 1, right? We've got ideally a 5 to 1, but the actual mechanical advantage is less than a 3 to 1, even if we put the high efficiency pulley in the first spot. Now let's put the high efficiency pulley in the last spot. So we've got 100 tension, 50% friction. We put our bad pulley right after the input. Well, 100, we've already dropped immediately to 50. Half that, we've got 25. Half that, we've got 11.25. And then take 90% off of that, which is, or 10% off of that, which is like just about 1. And then we end up with about 10 tension here. So let's do those numbers. 100 plus 50 plus 25 plus 11, or whatever the heck I said, 12 something. You get the point. 100 minus, 100 plus 50 plus 25 plus 12.5 plus, we'll call it 11. All right, we're down to below a 2.1. All right, so the important thing is to remember that the friction loss here multiply, not necessarily multiplies, but it has an effect throughout the rest of the system. So if I could lose as little as possible here, that means that there's more tension available in this leg, right, to go through the entire system. If I put a really bad pulley right at the beginning, I'm going to lose that input right away. So you want the most efficient pulley in the system should be at the, if you want the most output, that most efficient pulley needs to be right behind the input in the system. Sweet. Hope that made sense. Now let's move on to highline stuff, tension and vectors in multiple anchor points or high lines. Now this applies to rigging, speed lines, of course, but this also applies to climbing systems. You know, if you're on a high line hanging between two trees, okay, that's one thing. But another thing, if you're climbing with two climbing systems, or you're cradling a log, you've got two ropes on a log, you know, or a branch or something, you're rigging that way. So this will have an impact on that. Also, if you're suspended by your climbing line and suspended by your lanyard, all right, that's two anchor points. And we need to start thinking about the angle that we're making between these 2 points. And you'll see up on the screen here, we've got a scenario where we've got two anchor points. Can you see that? Oh yeah, sweet. So we've got a 100 load here, and we've got two. This is just one rope. It's one rope, two ropes. If they're terminated or it's just floating in the middle, it doesn't make a difference. I got these anchor points as close as I could together. So they're basically straight up overhead. And you can see with a 100-pound load, we've got 50 tension on either leg. They're equally supporting that load. There's basically half of that load being supported by each leg. And that makes sense. And I'll go back on screen here myself and say that if I'm a gymnast, right, on the rings, holding myself up in the air, you know, I can hang like this for a long time because I've got, you know, half of my body weight, you know, tension in each of my hands. Okay, so gymnast hanging on the rings, or if you're a tree climber hanging on like this, you've got a lot of reserve, because you're not. Each of your hands rather is only taking 50% of your body weight. Now, like in gymnast on the rings, when you start to move your arms outward, right, that gets a lot harder to hold yourself upright. Okay, and when you get to this point, these gymnasts on the rings like this, and they're shaking because they can hardly keep themselves in place. But you know, you go back to this scenario and you're relaxed again. So that'll be demonstrated. That'll be demonstrated on the screen here, because I'm not strong enough to do that on the rings. I know some people are, but just because you're suspended by two anchor points, the location of those anchor points in relation to one another makes a big difference on the force on those anchor points. Okay, so here we are, 50-50, basically just hanging underneath two anchor points. Now let's go to 90 degrees. And this is just an arbitrary number. It's easy to see if you can see, we've got 90-degree angle between the ropes where they meet at the load. And this is either one rope or two ropes, it doesn't matter. Now, over here, we're still sharing the load vertically. We have a vertical load or vertical force on this anchor point of 50, because it's just half and half of the 100 pounds. And just because of the math at this 90-degree angle and 45 degrees up here, it's 50 horizontally as well. But we have a peak force now, and the peak force is very easy to track because it just follows those ropes. The peak force is just over 70 pounds, okay, on each anchor point. So already those anchor points they're in the same location height-wise. There's the same amount of rope between them and the load, so they're taking they both have an equal load on them, but it's greater than the sum of the load itself. Okay, I hope that's making sense. So as we spread that angle out, these forces get higher and higher. So now let's go to 120 degrees. So remember, this will be on the test at 90 degrees here. You got about 70 on each anchor point. Okay, here is, now we're anchor points are in the same position, but we're just tightening up that rope. That load is moving higher. This angle is becoming greater. There's more force now on the anchor points, peak force anyway. Vertical force is always, theoretically, the vertical force is always just going to be 50, because each anchor, if you could put a scale underneath each of those poles or trees or whatever they were, they would just read an extra 50 pounds, because they're just, but this is, we're talking about torque now. We're talking about rope tension and vectors and torque, which has a very dramatic effect as we get higher and higher, and this angle gets wider and wider. So at 120 degrees, that's sort of the magic angle where the tension on each anchor is equal to the load, right? 120 degrees, 100-pound load, 100 pounds peak force on each anchor. You could see the horizontal force now is going up slightly. And as this angle approaches completely horizontal, then those forces will be the same, the vertical force and the peak force, but we'll never actually get there because it's impossible, nearly impossible to do. So let's jump from 120 up to 150. Now this is pretty realistic. A climber can certainly do this. In rigging as well, you could certainly do this with the GRCS or some sort of mechanical advantage. So here we are, we have a tensioned rope and a load hanging in the middle of it. At 150 degrees, we're just about double the load, peak force on each anchor point. This red arrow here, that's peak force, still only showing 50 vertically, but don't concern yourselves too much with that. There's a lot more going on here. And now we're jumping up dramatically, 187 horizontal force on those anchors. And now let's get real extreme. We're going to jump to 170 degrees, and you'll see quite a severe increase. All right, there's a 170 degree angle and nearly 6 times the load on each anchor, peak force. Okay, peak force 582 at 170 degrees, and horizontal force is nearly identical at 580. All right, significant when you talk about speed line rigging or creating a floating anchor for yourself out between some trees. You really want to make sure you've got some anchor points that can take that load, and also your equipment, because now that rope is under tension as well. Now that rope itself is under 582 units of tension. All right, we don't add the anchor point force into the rope. The rope is under 582 tension, but each anchor point is under 582. That's pretty severe when you think about tying into some spindly tall trees to try to get over this dead one you're working on. That's quite a lot of force pulling those trees together. So a takeaway from this as well, that a practical application of this, these physics here. So looking at that last one, that 170 degrees, and that 100-pound load in the middle of it, putting almost 6 times the tension in that rope. Okay, that's useful when you want to pull a tree over, for example, or when you want to tension a porta wrap. Okay, we've got my rope ended up a little short here, but we have a porta wrap. This rope is tied to a log, and we want to tension that porta wrap, right? And everybody comes over and, hey, everybody, come on over here, help me. Let's get 3 people jumping on this thing. And everybody wants to, 1 second. See if I can pull my house apart here while I'm at it. All right, so we've got anchor point, load tied on. This is the rope coming down into the porta wrap. And we all want to jump on this rope and pull straight down, and we get all our friends over to pull on this rope. But based on the physics that we've seen here and tensioning or vectoring a tensioned line, that's a very good word to know. Okay, if I vector this, right, I'm putting an incredible amount of force, a incredible amount of tension into that line just by vectoring it like a bowstring. All right, that's how you should be tensioning your porta wrap, right? Vector it, and then somebody pulls in the slack as you let off, right? Get a couple people, vector that, yank on it, and then pull it through the porta wrap as that tension comes off. You got to get the wraps just right. You don't want to lose it, but you don't want too many wraps. There's too much friction. Okay, that same idea applies pulling a tree over. All right, anchor that line to the top of the tree, anchor it down to your anchor point, stump, or whatever the heck you're using, and you can vector that line and create a much more force than if you were just pulling on it directly. All right, and I'll take that one step further, and I know we've got just a few minutes left. So, of course, when you vector, just take everything I say with a grain of salt, because when you do, if you are pulling a tree over and you do vector, okay, yeah, you're moving the rope off center line with the direction of fall. That, depending on how good your hinge is and all that, you got to think about that stuff. But generally, it shouldn't really create too much of a problem for you. But hey, everything comes with a caveat, right? But remember, tension the line and then vector it, yeah, or hang on it. If there's enough room between you and the tree, get some people to just hang on the rope. A couple of you hanging on it together, you can create a tremendous amount of tension in the leg of rope. So I'll bring that back again to the fiddle block or block and tackle. Same idea would go here. Let me get this out of the way. Okay, bear with me. We're doing pretty well on time. Here again is my fiddle block. It's attached, basically attached to the tree up there or onto a rope. We've got it anchored back here. Now, we've all learned that if you want the greatest efficiency out of your fiddle block or mechanical advantage, you want to pull in line, right? So yes, it is true, I'm getting the maximum amount of efficiency here if I pull in line with these ropes. Okay, if I pull out of line here, I'm losing some efficiency. But if this is in a tensioned system and I walk away at a 90-degree angle and now I pull, I get the mechanical advantage plus I get the vector, right? I get the vector in that tension line, and I can overcome a lot of, say we're just pulling, we just can't get this tree to come over. What the heck is going on? We don't have any more power. Think about if there's the safe margins for it. Think about just walking out and going pulling 90 degrees perpendicular to that tension rope, and you'll vector that rope along with the mechanical advantage, and vectoring that rope, you can maybe get that tree to come over. Increase force very dramatically, as we saw in the computer program there. So looks like we got about 5-10 minutes left. That's all I have at the moment. So should we just open it up for questions, Cale, or?
All right, I do have a few questions for you here.
Cool.
Aaron Jones has asked, talking about your system with the multiple anchor points, if a difference in elevation between the two anchor points is going to make a difference.
Yes, it does. And unfortunately, the system that I'm using, well, let's just see what happens, because it'll tend to equalize the load. So let's try it on a single rope, and then maybe I can attach 2 separate ropes, and we can give it a go there. So you'll just bear with me, and I can build that system. It'd probably just take 2 minutes. And you can show it on screen if you want while I'm building it.
while you're doing that, what is the name of this program?
This is called V-Rigger. This program is called V-Rigger, just VRIGGER.com. And you can, it only works for, it's a Windows-driven program. I run a Mac, which is, it's a long story. You can run it on Mac, but I wouldn't recommend it. Just get yourself a Windows computer. But the, vrigger.com, and I think it's like $300 or $280 or something like that. It's pretty reasonable, and you can do a lot of cool stuff with it. It's a great instructional tool. Let's just see right now. So what I'm doing is just getting some stuff out of the way here. I'm gonna let's go to whatever, 150 degrees ish, and then I'll drop one of these anchors a little bit. All right, and then I'll calculate the forces. Everybody see that?
Yep.
All right, so you see that the load shifted closer to the lower anchor. We still have, it looks like we still have equal tension. We have 268 tension throughout the rope itself. If I check this anchor, we've got a peak vector or a peak force of 268, which would be the rope tension, 268 here as well. But the horizontal looks like 264, so that's the same. The difference being that the load has shifted, so our angle should be slightly different, which here it's 79, here's 79, so yeah, interesting. Let me drop it again, and of course this is just sliding on one leg of rope. It's not two separate ropes. So again, here closer to that anchor point, now our angle has increased a bit, so our tension in the rope went up, but we're still showing the same angles and same force on each. So that's I can't really. My math isn't good enough to talk anymore about that, Aaron. Sorry. But it looks like, at least in the computer simulation, that they're about the same. Now, I would imagine that the closer you get to a certain anchor point, the more force you would be placing on that anchor point in a vertical plane. But
go out and try it.
Yeah, we got to go out and try it, I guess.
Let us know, Aaron. I have another one here.
Yep.
Joshua Frisco Farmer Osttot. I would put everything up here, but Facebook is currently not working for me, so I can't get those comments. Joshua is asking if pulling at a 45-degree angle is going to work any different if you're pulling from the load side of a mechanical advantage system versus the anchor side.
I'm not sure I understand that question. Say it again.
Is pulling a 45-degree angle going to work the same or better if you're pulling from the load side versus the anchor side?
Yeah, I'm not sure I understand. We would have to maybe mock it up here. If we have a load suspended and we're pulling, so if we have a load suspended here, Is that what we're getting at? And I'm pulling, and I have a 45-degree angle here. Is he? Are you talking with him right now? Am I tracking right?
He hasn't responded or anything yet. We can move on to something else.
Yeah, I'm gonna just build this other. Keep building the system here.
Okay.
And we'll see what happens when we connect 2 ropes. Oh my gosh, this computer is so terrible. Come on.
Hey, that doesn't look right.
There we go. All right, now we've got a load, and this load, we'll see how much it weighs. Properties, force is 100 pounds, good. Now let's calculate. Okay, so there's a difference now when the load is connected with 2 different ropes. We're gonna show rope angle. Funny that it's not showing that angle. All right, 2 separate. All right, so this is tensioned, separate tension on these ropes, so the load is not floating, and that is definitely having an impact on the difference between anchor points. So here, 170 pound peak force, 162 peak force, lower anchor point. Vertical force 30 pounds, horizontal 159. Vertical force here 69 pounds. So yeah, when you've got two tensioned ropes and a load and differing levels of anchor points, that certainly has an impact. We'll go a little closer here. Yeah, interesting. Let's go up. Right, so that smaller angle is reducing force, but you can have differing levels, differing loads on each anchor. So here the load is much closer. It's a 100-pound load, much closer to this anchor point, 92 pounds. We'll just mess around and see what we come up with. 86 and 31, so not much tension on this right side anchor at all. Just kind of messing around in real time here. There you go. Now with the lower anchor on the left and much higher anchor here, even though the load is closer, we've got more tension on this leg. So somebody with a physics degree could explain a little more about that, but that's go ahead, Cale.
From what I'm seeing, well, I'm assuming here that is coming from the fact that the angle is wider. So this, the length of the rope doesn't really matter, but it's that angle from vertical that you were talking about earlier that's going to cause that peak vector to be different.
Yeah, I think when we're talking about two separate tension lines with different anchor point heights and distances, there's a lot more at play. You've got rope angle, and you've got how close the load is to each anchor point, and the angle that rope makes between the anchor point and the load. I haven't experimented with that a lot. That's very interesting. I should do a little more on that for next time. But yeah, cool stuff. Like I say, I can't explain that with my current state of mathematical affairs. But a couple links that I forgot to mention. And shoot, I didn't type them up either. Check out the HSE, so UK website, HSE, the Health Services Executive. Tree Imagineers were involved, or Chris Cowell and Andy Detter and some other folks were involved quite a while back in evaluating current rigging practices. So check out hse.gov and look up evaluation of current rigging practices, or if you go to Tree Imagineers website, treeimagineers.com, you'll be able to find that in their links or downloads section. It's a very long book, as it were, about 300 plus pages, but there's just tons of awesome information in there about peak loads, negative blocking, things that we couldn't really get into today. Also, Richard Delaney's Rope Test Lab. If you go to ropelab.com.au, you'll find Richard Delaney's Rope Lab website. Absolutely fantastic. He's got some mechanical advantage tests in there that are just super if you want to continue to go down this rabbit hole and learn more and become more proficient in rigging and building mechanical advantage systems. So I would give a shout out to those folks. Certainly have had an impact on what I'm doing here. And yeah, I think that's it. We're closing out, but I want to thank everybody that hung out and participated. Awesome, great, lots of great questions, and I hope that it was helpful. And if you, I'm probably opening myself up to a can of worms here, but you can hit me up on Facebook Messenger or email me, taylor@dmmwales.com, if you have some questions. Obviously, I can't answer everything. Either I don't know myself, but I can get you pointed in the right direction, or maybe I got a day job, so I can't probably talk too much, but I'll help you out as much as possible. And yeah, thank you very much, and thanks to DMM, a company I work for always supporting, and we're doing our best to try to reach out and keep education going, and there'll be more of this in the future. Learn more about our products and things like that too. So. Once again, big thanks to Kale and Carson and Nick at TreeStuff. Really appreciate the opportunity.
All right.